Hello everyone, my name is Tillman Milzo, or just Till, and today I'm gonna talk about caterpillars hiding in tunnels, or long paths in line arrangements. Okay, this is joint work with Udo Hoffmann, who was at TU Berlin and is now in Brussels, and Linda Kleist, who is still at TU Berlin. Okay, so these are my co-authors. This is Linda, this is Udo. We did this work in Berlin. You can see here the Fernsehturm, so it is in Berlin. These are some kind of drawings of line arrangement and paths. And yeah, Udo and Linda, me doing weird faces. Okay, let me tell you what is a line arrangement. A line arrangement is a set of lines in the plane. And they form a graph, namely any two vertices that meet, they form a vertex, and we assume that no three lines go through one point, and an edge is the bounded segment between two vertices. We would also consider these rays as edges. They're kind of dangling on one vertex and they're not connected by two. You could imagine kind of a point at infinity and all these edges are connected to that one. And there's another edge, and faces would be regions bounded by edges, but also unbounded regions, so infinite regions, also called faces. Here's another face, and this would be an unbounded face, so it would go here to infinity. And so we also have a dual graph, and we care for long path in the dual graph. So the dual graph would be defined by all the faces, and two faces are adjacent if they share an edge. And this would be here a pretty long path in the dual arrangement. And so this is a talk about we want to find the long path, and what does it have to do with caterpillars? Stay tuned, and we'll figure out. Okay, the one thing you should know about this line arrangement is that the number of faces roughly n squared divided by 2. This is a well-known result you can look up anywhere. Yeah, n will denote the number of lines for the rest of this video. Okay, so we also talk about alternating dual paths. Alternating dual path will be where the lines are colored red and blue, and we have to cross alternatingly a red and a blue line. So we first cross red, blue, red, blue, red, blue, and so on and so forth. Yes, and so let's see related work. There's one paper in it, first published on CCCG 2013 by a lot of people, and then the German version appeared 2014, and I think Ferran Hurtado originally posed this question. Okay, so what are their results? They showed that there always exists an alternating path of lengths, of linear lengths, and they said this is tight. If there's just one blue line, there would be only a linear number of blue edges, and that's it. So how do they get their lower bound, which is more interesting? Well, they show that the graph is connected. Like if I want to go from one cell to another, then this from one bichromatic cell to another, then I can always do this. And they're just these cells which are far away from each other. So that's it. For monochromatic path, they show essentially n squared over 4. There exists always a path of length n squared over 4. And they upper bounded by n squared over 3. So remember that I told you that the total number of faces n squared divided by 2. So basically they say you cannot traverse more than 2/3 of all the faces. And the idea is just there exists this example where 2/3 of these faces are black and 1/3 of the faces are white, and only white and black faces are adjacent to each other. So yeah, it's well known that this graph, the dual graph, is bipartite, and there are kind of shifted examples where more faces are black than white. So this would be their upper bound for monochromatic. path is. Okay, so what is our result? So we can improve their example. So their example was with one blue line and all the other lines are red. But what about the number of red lines and blue lines are equal? Well, we don't know. Actually, we believe that as soon as you go to even the same number of red and the same number of blue lines, you will probably have a quadratic number of your path will get of quadratic length, because then just some structure will blow up. But what we can show is, at least if this is pretty balanced, like 2 in red and 3 in blue, then we still have a upper bound of O of n. We can of the longest alternating path in the worst case. So we give this example where this happens. So then for the monochromatic path, we get that there always exists paths of length n squared divided by 3. And remember, they gave an upper bound of n squared divided by 3. So for monochromatic path, we got tight. So this was kind of our most tedious technical contribution, and kind of the nicest results in that sense. But really, actually, we worked much more on this part. And then our third result is, so kind of our intuition was that usually you get much longer paths than in this specific example, and we can make this statement rigorous by looking at random coloring. So in random colorings, for any arrangement, we get paths of length n squared divided by log n. So this is almost n squared, with high probability, of course. Okay, so for the rest of the talk, I will give you the proof ideas for those results. So we start with a monochromatic case, monochromatic arrangements. Here the result is that we get n squared divided by 3 minus some lower order term number, length of longest path. This is 2/3 of the phases. So for us, really interesting is only that these are 2/3 of all the phases. Okay, let's see how we do this. So the overall idea is that we define something called levels and something like tunnels between levels, and then we will route our paths in these tunnels. And the good thing is that the tunnels will be disjoint of each other, so we can really route in between here. So this is the overall idea. So let me tell you what are levels. Levels is a standard term for people dealing with line arrangements or hyperplane arrangements, but maybe you don't know it, so now you can learn it. So level 0, that would be all the edges and vertices which have no lines below. So all these here have no lines below. Level 1 would be those which have one line below. So this segment here has one line below, namely this one. You can't see it, but it would extend here. And level 2 is 2 lines below, and so on and so forth. And yeah, if you have 5 lines, you get 5 levels. Oh, if you have 5 lines, you get 5 levels. Yeah, level 0 to level 5. Okay, sorry, 6 lines, 6 levels. Yeah, we can see here. Note that as the lines are monochromatic, I just colored the different levels. So the even levels will be always red in our case. So, oh yeah, and between level 0 and level 2 will be our first tunnel, and between level 2 and level 4 will be our second tunnel, and then above all is tunnel 3. And as I already mentioned, we route our paths in these tunnels. Sorry. Okay, so to make life easier for us, we use a simplified drawing called wiring diagram. So as we care only about the graph and not about the actual drawing, this kind of drawing will be more convenient than drawing is at straight lines. Yeah, so here again are our levels in red, and the tunnels are in between. And so yes, this is how the path would look like. It just goes from one tunnel to the next and so on and so forth. And then we can just add all these lengths together and we get n squared over 4 just by adding all the lengths together of for each tunnel we can give a lower bound on how many lines must be crossed, and this gives this number, which is a previous result, but we get it in a much simpler way. But recall we want to get here a 3, not a 4, so we have to do more work. So let's have a closer look at one of those tunnels. So here these are the tunnel boundaries, and we know that we have degree 4 because we have, you know, each vertex corresponds to 2 straight lines crossing. And then we define these good vertices, which are just all these vertices, and wall edges. And for each face which is bounded by a good vertex and a wall edge, we call it a good face. And all the other faces, they're called bad faces. And it is somehow an easy observation that our path within one tunnel will use exactly all the good faces and avoid all the bad faces. So the bad faces are somehow just incident to one tunnel side, whereas the good faces have an edge on one tunnel side and a vertex on the other. And this comes from this alternating level, which goes up and down here, or maybe stays down, or maybe stays up for some time. Okay, so what we want to do is we want to reroute to get our path longer, because our path were not long enough. So the idea, one of the first ideas is to look at bed faces between two tunnels. So this is a top tunnel, a bottom tunnel, and here are a lot of bed faces. And then we can argue that there must be also a lot of bed faces on the other side of the tunnel, and they must all be adjacent. And then we can argue that we can reroute and forget about this edge. And we just do this as often as we can. And after this, there will be no adjacent bed faces anymore. Okay, and the hope would be that we're done. And to prove that we're done, right, so we want to route our path going through 2/3 of all the faces. This means for every unused face, there would be 2 used faces. So the idea is that for a bad face, we give 2 charge, and we can charge, distribute this charge to 2 used faces, namely to the most left wall edge and the most left wall vertex. The problem is that double charging can occur. If double charging would not occur, we would be done, because then this would show that we use only 1/3 of the faces were not used. So, but double charging can occur, and after a very careful analysis, we can show that the only way that double charging can occur is if a used face is charged from one bed face from the top and one bed face from the bottom. And then it would look roughly like this. And then we could reroute again. So our charging scheme also tells us how we have to can reroute. Yeah, I'm hiding here a lot of technical details, but this is how it looks like. Yes. But then we're done. So then the number of used faces is 2/3 of all the faces, and 2/3 of all the faces n squared over 3. Yeah, so this was very technical, and the main where the main technical effort went into. But really, these two pictures were for us a breakthrough, and we didn't anticipate actually it was going to be so technical. Okay, and now there's a 3, and we are happy. So let's go to the other results. A much easier result is that the longest alternating path in a random coloring have length n squared over log n with high probability. So let's see how this goes. And the idea is the same, but here we just use tunnels which are much wider of length k, and k will be roughly log of n. So, and the thing that we have to do here is we just have to guarantee that we can go from left to right within one tunnel, and then just counting will do the rest. So how do we go from left to right in one tunnel? So let's assume there would be something blocking, so we can't go from here to there, so there must be something blocking. And then the end vertices of this blocking structure, they must have the same color, and all the, all this must have the same color as well. So there must exist k blue separating lines. So what we do is just we count all the possible events that this can happen. So we know we have at most n squared vertices, because we have n lines, and any two lines only induce one vertex. And then we know that there are only n to the 4 pairs of vertices, and this creates these bad events, n to the 4 bad events. But each bad event is very unlikely, because you need something like theta of log n. Many items must be all colored the same, and this must happen in one of the n to the 4 cases. But if you choose your constants good enough, so these widths large enough, then with high probability, none of these events take place, and we can find a path in each level simultaneously. And then we just have to do some stuff to add these paths together. It's gonna be a little bit technical, but it can be done. Okay, so this was this idea. So now let me go to the low bound example. So this is what we worked longest on, but it's actually what was in the end the simplest. So we show you 2 in red and 3 in blue lines, such that any alternating paths have length at most O of n, with a small constant here hidden in this O of n. So okay, we start with n-gon for n divisible by 3, and then we just a regular n-gon, and then we use all the extension lines of all these sides of the n-gon. And then we draw all these helper lines here, and then we somehow, as I said, this n must be divisible by 3 here, and we add between any third cone, we add two lines which are blue. And then what will happen is, because in these 2 cones here there are no blue line, it is impossible to form a path to go from here to there. So the only thing you can do is you can stay within. And you can also not go forth and back here, because these there will be only you have to look at this cone, but there are not enough blue lines so that you could go forth and back, so you can only go out or in. So the only thing that remains is you can go from the outside to the inside, then make a round tour here, and then go out again. And each of those 3 parts going to be linear, and so the total length is linear overall as well. Thank you for watching the video. So these were the 3 main results. This lower bound example, which is kind of balanced, and then this rerouting through the tunnels. Thank you for your attention, and